An electrocardiogram, or ECG, or the Dutch or German version of the word EKG, is a tool used to visualize the electricity that flows through the heart. An ECG tracing specifically shows how the depolarization wave moves during each heartbeat, which is a wave of positive charge. And the way it looks depends on the set of electrodes you're using. This particular set of electrodes is called lead 2, for example, with one electrode on the right arm and the other on the left leg. So essentially, when the wave's moving toward the left leg electrode, you get a positive deflection, like this big positive deflection corresponding to the wave moving down into the left and right ventricles. To read an ECG, there are a few key elements to keep in mind. And one of those things is looking at the intervals. In a typical waveform, there's a P wave, a QRS complex, and a T wave. In addition to that, though, there are certain intervals like the PR interval, the QRS complex itself, and the QT interval. The PR interval spans from the beginning of the P wave to the beginning of the QRS complex, and it represents the time from the beginning of atrial depolarization to the beginning of ventricular depolarization. It's normally about 0.12 to 0.20 seconds, which is 3 to 5 little boxes, since each box is 0.04 seconds. So the PR interval shown is about 4 boxes, or 0.16 seconds. Any deviation in the normal depolarization pathway from the SA node to the ventricles can change the PR interval. For example, if the atria are depolarized by an ectopic atrial focus, for example, an irritable atrial cell outside the SA node. If this ectopic focus is farther away from the AV node, it'll result in a longer PR interval, because the signal has to travel a greater distance. Alternatively, if it was really close to the AV node, the PR interval might be super short. Another example is first-degree heart block, where the electrical signal travels more slowly through the AV node than it normally does, and this causes the PR interval to lengthen beyond 0.2 seconds. Now, the QRS complex represents depolarization of the ventricles, and it's normally less than 100 milliseconds, or 2.5 little boxes. Just like the PR interval, the duration of the QRS complex can change depending on the path from the AV node to the ventricles. For example, if an ectopic ventricular focus like an irritable ventricular cell fires off, the resulting depolarization wave will move slowly from muscle cell to muscle cell, instead of traveling quickly through the electrical conduction system. Therefore, it ends up taking a longer time to depolarize the ventricles and the QRS complex gets wider. It's often considered intermediate if it's 100 to 120 milliseconds long, and prolonged if it's over 120 milliseconds, or 3 little boxes. Finally, the QT interval spans from the beginning of the QRS complex to the end of the T wave, and it represents ventricular systole, meaning the entire span from depolarization through repolarization. Normally, the QT interval should be less than half a cardiac cycle. In fact, for a heart rate of 60 beats per minute, the QT interval is generally considered to be abnormally long when it's greater than 440 milliseconds in men, or 460 milliseconds in women. Let's say that you measure someone's QT interval at a different rate though, say 90 beats per minute, and it ends up being 400 milliseconds. You might think that based on what we just said that'd be considered normal, but you can't really use this to compare to the values at 60 beats per minute, since the QT interval changes depending on the rate. As the rate increases, the QT interval decreases. So at 60 beats per minute, the abnormal cutoff might be 440 milliseconds, whereas at 90 beats per minute, it's likely something lower. So what we have to do is find the corrected QT interval, or QTC, at the different rates so that you can compare it to the QT interval at 60 beats per minute. Even though there are several formulas you can use, the Bizet's formula is probably the simplest, where the corrected QT interval equals the QT interval in milliseconds divided by the square root of the R to R interval in seconds divided by 1 second. As a bit of a side note, usually this formula is expressed without the divide by 1 second bit, but the astute observer will notice that the units won't work out if you don't divide by 1 second. Alright, so let's use our 90 beats per minute and 400 millisecond QT interval from before, and also assume that it's a male. If we plug in 400 for QT and 90 beats per minute, which is the same as 0.66 seconds per beat, we have a QT of 400 milliseconds divided by the square root of 0.66 seconds over 1 second, which is 400 milliseconds divided by 0.81, which remember is unitless. And so we get a corrected QT interval of 493 milliseconds. Now if we compare this to the value at 60 beats per minute, we can see that the corrected QT interval is actually greater than 440 milliseconds, which means that this measured QT interval of 400 milliseconds at 90 beats per minute is actually abnormally long. Now, the QT interval can be prolonged due to medications, like amiodarone, which is an antiarrhythmic that affects cardiomyocyte ion channels, but it might also be inherited, where there are mutations in genes like LQT1, LQT2, and LQT3. One of the most feared complications of having a prolonged QT interval is a type of ventricular tachycardia that can lead to sudden cardiac death, called torsade de pointes, where the ECG shows a twisting of the points. Alright, as a quick recap, an ECG waveform has a PR interval that's usually 120 to 200 milliseconds, a QRS complex that's less than 100 milliseconds, and a QT interval that's less than 440 milliseconds in men and 460 milliseconds in women. But it's important to remember that these are the rates at 60 beats per minute, and the Bazette formula can be used to find the corrected QT interval to compare to rates other than 60 beats per minute.